Okay, people, continuing along. So we're going to take a Lindemann-Hinchelwood type mechanism and apply it to a realistic example involving three bodies. So we call that a termolecular reaction. And it's going to have the same approach as our Lindemann-Hinchelwood mechanism. So here is our realistic reaction. So this is the overall reaction observed here. O triplet P, so that's a ground state oxygen, plus O2 plus M, right, which is our collisional body, to make O3 plus M. So looking at the mechanism, you can see here in the first step, oxygen atom reacts with O2 to make an unstable O3 or an excited O3, which could, right, decompose back into its original reactants, or it could be stabilized from the collision of a third body and move on to form products. And then, of course, M star is eventually stabilized back to its ground state. So this triplet P thing, that's what we call a term symbol. So O triplet P is the ground state. We'll talk about what triplets and singlet states are in a lot more detail in 362. But a triplet state is two unpaired electrons. Okay, so if you recall, right, the electron configuration from oxygen atom as a ground state has got 6 valence electrons, right? The 2s is all paired up, and then we go 1, 2, 3, 4. So there is our triplet state. O singlet D, which is the first excited state, exists in this singlet, which is an electron pair. Okay, and so that first excited state of oxygen atom looks like this. It still has its 6 electrons, but now instead of spreading out, they're forced to pair up. So when we look at this mechanism specifically only happens, at least only happens reasonably, with the triplet ground state for the following reasons, right? If we look at our Lewis structure, right, there's our oxygen atom with our 6 electrons. And if you recall, O2 also exists as a di-radical, even though we draw its Lewis structure looking something like that. So because both O2 and O are ground state triplets, so they both have unpaired electrons, they can undergo this fishhook mechanism, right? So now this is where we get this O3 star. So I'm going to draw it with like this kind of like partial bond, right? Something like that. Okay, so this is our unstable O3, which could just reject the electron and go right back to the 2 reactants, or from stable collisions, right, it could end up forming the finally observed O3. Okay, looks something like this, where all of the electron pairs have been satisfied. Okay. So, and certainly, of course, depending on the rate of inhibition and the rate of production, right, depending on if it's in the high pressure limit or the low pressure limit, that's going to dictate the mechanism and the kinetics that are observed. So if we look overall, I'm going to call this K123 to symbolize a third order reaction. And if we think about what the overall rate would be just from this top reaction, not from the mechanism, but just from the overall reaction, okay, we would write it something like that. K123, the third order rate constant, times the ground state oxygen atom, times O2, times M. So let's keep teasing out the rest of these rate laws, and let's see what we get when we look at the mechanism. Okay, so we'll write the rate law for O3 star, our intermediate, right? So I'll just point that and say that is I, that's our intermediate. And then here, instead of using 1s and 2s, I used A's and B's just to mix it up a little bit. So the production of O3 star is going to go Ka times O times O2. So it can also decay in the inhibition step. So that's minus Kb times O3 star. And then, of course, it can appear in the production step. And that's going to, or it decays in the production step minus Kc, and that's going to be times O3 star times M. And we're going to apply the steady state approximation to this thing, because that is a reasonable thing to do for this mechanism. And when we do that, so doing some algebra, we get an expression for O3 star, which is going to go as the following. So that's going to be Ka times O times O2. And then that's all divided by Kb plus Kc times M. And then now, noting that if we go back to what our dO3 dt looks like, but this time we're going to put that together from our mechanism, not from our overall rate. That was Kc times O3 star times M. And now we can plug the steady state approximation for O3 star into the rate law for dO3 dt, and that's going to give us an expression that's much more useful. So that ends up becoming the following. So I'm going to keep the Kc and the M separate, and then now we'll plug in O3 star here. Okay. So from that we get Ka times O times O2, all divided by Kb plus Kc times M. And let's see here. I think that I may have done the algebra on this thing. Yes, so I'm going to go through into the next page, and we can rearrange this, by distributing the Kc times M, which gives us the following. So continuing along with that, right, we get dO3 dt equals, so distributing that through and doing the algebra yields the following: Ka times Kc times M, all divided by Kb plus Kc times M, all times O, all times O2. And if you recall from our original description, so here I've got like the overall reaction written right here, right, which we said would take place with rate constant K3. Hopefully what we can recognize from this, though, is this would all have to be a second order reaction based on what we've written here, right? So this looks like a second order K. And I'm going to denote that as K2 for second order, right? So now we'll play the same game where we look at this in the high pressure limit and we look at this in the low pressure limit. So low pressure limit, and then our high pressure limit. Okay, so in our low pressure limit, our M is small, right, just like before, and on our high pressure limit, our M is large. And so now what that means for this expression here, if I start comparing these rates, Kb is going to be much, much greater than Kc times M, because M is small. Thus, we can ignore Kc times M, and what we end up with in the low pressure limit is the following: dO3 dt ends up being the following. So let's see, we're ignoring Kc right here, so we're just left with Kb. And now that all goes as Ka times Kc, all divided by Kb. And we still have that M up there, right? So now that's times M times O times O2. And lo and behold, check that out. That, because there's M times O times O2, all of this combination of rate constants has to be a third order rate constant. And thus, in the low pressure limit, this reaction looks like a third order reaction. So in other words, M, the amount there, is important. Okay, so now what about in the high pressure limit? Well, it's the opposite, right? Kc times M is much greater than Kb. So we can ignore Kb right here. And you can see the Kc times M and the Kc times M all cancel. And what we end up with is dO3 by dt. So again, we said Kc times M and Kc times M cancels because we're ignoring Kb. And now that just goes as Ka times O times O2. And you can see Ka there has to be an overall second order reaction. So this was very similar to the general Lindemann-Hinshelwood mechanism, but now when we put it like a real reaction in there, a reaction that actually would have to involve a third body, the game worked out to be the same way. Under the low pressure limit, we get the higher order reaction, which is to say the concentration of M matters on the low pressure limit. But in the high pressure limit, M is sufficiently large enough that it no longer matters. And we can really think of the product of our overall rate constant times the concentration of M as this effective second order reaction. So in other words, K2 appears to be K3 times the third body concentration N. Okay, excellent. And so there's several other specific systems that we could apply this Lindemann-Hinshelwood type mechanism. However, I only wanted to look at one specific example here. Okay, I'll see you in the next videos.